Okay, question one. The curve y equals a cos bx plus c, where a, b, and c are integers, passes through these points, and the curve has got a period of 2 pi upon 3. Find the values of a, b, and c. Well, essentially, we need to understand what those values of a, b, and c represent. So I'm going to do that right now. I'm going to try to explain to you. So let's go in reverse. Let's start with c. What does c represent? It represents the center line or the shift in y. So if we've got a sine or a cos graph, right, and let's say the c value is 3, that means the entire graph has been shifted up by 3. And so the wave kind of oscillates above and below the line y is equal to 3. Okay, that's what c represents. B, what does that represent? Now, this is the one that causes the most confusion because students think it means the period. It's not the period, but it is related to the period. So what is it? B is the number of waves in 360 degrees or in 2 pi radians. Okay, so let's just have a think about that. If the value of B was 3, then that would mean that there are 3 waves in 2 pi. So how big would each wave be? Well, it would be 2 pi divided by 3. Let's try another one. Let's say that B was 5. That would mean that there would be 5 waves in 2 pi. And so how big would each wave be? Well, it would be 2 pi divided by 5. So we can see that the period, right, which is like how long is each wave, is going to be related to this number b, and it will be through this equation here, right? 2 pi upon b, right? And that should kind of make sense because if I've got, let's say b is 7, right? There are 7 waves in 2 pi. So the length of each wave, the period, will be 2 pi divided by 7. So in this particular case, right, what are we told? We're told that the curve has got a period of 2 pi upon 3. So we can just rearrange this formula. And we can say that b will be equal to 2 pi divided by t. And so if we just substitute in 2 pi upon 3, so we're going to have 2 pi divided by 2 pi upon 3, then that's going to be equal to 3, right? So our value of b there is going to be 3. Well, lastly, what is A? Our A is the amplitude of the wave. Amplitude. It's kind of the height that the wave goes above the center line or how far it goes below the center line to the trough, right? So if the amplitude is 5, right, then what it means is the wave goes up by 5 from the center line and also down by 5 from the center line. Okay, well, how can we move on from here? Well, we now know that b is 3, right? So we know that our curve is going to look something like this. So a cos 3x plus c. And we're given 2 points. So the first point is negative pi by 6 and negative 2. So we can substitute that into our equation. So if I substitute negative pi by 6, right, I get a cos 3 times by negative pi by 6. So I get negative 3 pi by 6. And of course, that is the same thing as negative pi by 2, right? Plus c, and the y coordinate for that was equal to negative 2. Okay, then, well, what is cos of negative pi by 2? Well, we could key into a calculator, but it's also the same thing as cos of pi by 2, right? And that's going to be equal to 0. So I get here that c is equal to negative 2, right? Because this whole thing here is 0. Okay, then, so now I know that y is equal to a cos 3x plus c, okay? And that c is equal to negative 2. So I can now substitute in the other point, and the other point was pi by 9 and a half. So y is equal to half, and x is equal to pi by 9, right? So I get 3 pi by 9, which is the same thing as pi by 3, minus 2. Now, what is pi by 3? Pi by 3 is, what is cos pi by 3? That's going to be equal to a half. Let's say that you don't have your calculator and you want to kind of understand why that is. Essentially, what you want to do is you want to memorize this triangle, right? So here what we got is we got an equilateral triangle. So these angles here will be 60 degrees. I've cut it into half to make a right angle there. And this is 30 degrees. And let's say that the equilateral triangle has got side lengths of 2. That means that this length here is 1. And using Pythagoras, I could get that that length there is square root 3. Okay, so that's how we construct the triangle. I'm just going to get rid of this. Okay, well, that means that I should be able to see what cosine pi by 3 is, or cos 60, right? Because cos 60 degrees will be adjacent, which is 1, divided by hypotenuse, which is 2. So we get cos 60 is a half. So for those of you who've struggled to memorize the sine, cos, and tan of the critical angles, and I know that you're not going to have a calculator moving forward, right? I suggest that you try to memorize the triangle like that as a way of remembering. Okay, so we have got a half is equal to a times by a half, so a times by a half, minus 2. Okay, and so if I add 2 to both sides, I get 5 upon 2 is equal to a upon 2. And that means that a is equal to 5. Okay, so our final curve is going to look like 5 cos 3x and then minus 2. Okay, what's that going to mean? It means that we've got a curve which is shifted down by 2, which has got an amplitude of 5, right? So it's going to go up and by 5 and down by 5. And there are going to be 3 waves within 2 pi radians. Well, we can then use that knowledge to answer part B of this. So we want to find the least value of y on the curve between x is 0 and pi by 2 and state the value of x at which this occurs. Okay, well, there are a couple of different ways we could do this, but why don't we just sketch the graph as well, just so that you can see what I'm doing. So I'll draw an axis like that. So this would be like 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, something like that. Okay, so if we've got the curve y is equal to 5 cos 3x minus 2, we know that the whole curve has been shifted down by negative 2, and so that's going to be like the center line. So y is equal to negative 2 is going to be the center line of our curve. Okay, and the amplitude, right, was 5. So we're going to go up by 5 from negative 2. So if we go up by 5, we're going to go up to positive 3. So the curve will go all the way up to there. And where would it go down to? Well, from negative 2 down by 5 is going to take us to negative 7. Okay, so I'll just label that on, right? This is negative 2. This is negative 7. This is positive 3. Now, the cosine wave, right, starts all the way up here at the top. And I'll try to draw like one full wave like that. I'm not so good at doing this, but never mind. Okay, like that. So that would be one full wave, okay? All right, and crossing the center line at those points there. Now then, we learned earlier that b is 3, and that corresponds to a period of 2 pi upon 3, right, which is what we're told in the question. So a period of 2 pi upon 3 means that the length of one wave is going to be 2 pi upon 3, right? So that's 2 pi upon 3. And so therefore half a wave is going to be pi upon 3. Okay, and we think, well, what's the lowest value that this wave can get to? Well, the lowest value you can get to is down here, right, which is negative 7. And so we can see that just now by looking at the graph, which is quite nice. And is pi by 3 within the range of 0 and pi by 2? It is. So we know that, that this is going to be our lowest value. And so hence we can say the min value of y is equal to negative 7. Okay, so that's a way of doing it graphically, and I've done that not necessarily because it's the simplest way, but just because it helps you to see, right, the full picture, what A, B, and C mean, how we can use it to sketch a graph, which they often ask you to do. So why don't we just do it now in a slightly simpler way? We could do it through differentiation if we wanted, or we could just do it by thinking about the property of sine and cos. So y is equal to 5 cos 3x minus 2. Well, let's just think about that cos, right? What is the biggest value that a cos graph can take? It's positive 1. And what's the lowest value that it can take? It's negative 1. So the lowest value is when cos x, or cos 3x, it doesn't matter, is equal to negative 1. So let's substitute that in. We will get y is equal to 5 times negative 1 minus 2, which is negative 5 minus 2, which is negative 7. Okay, so there we go. We can do that. The trouble with that method is we're not necessarily sure if that value does occur within this range of x, but then we could go back and check by using the graph if we wanted to. How could we use differentiation? Finding the lowest point is the same thing as finding a stationary point. So if we've got 5 cos 3x minus 2, we differentiate that, so we get y prime is equal to negative 5 sine 3x, and then we'd have to times it by 3. If we differentiate negative 2, we get 0. And we've got a stationary point, which is a minimum, when y prime is equal to 0. So we're trying to solve 0 is equal to negative 15 sine 3x, which is the same thing as trying to solve 0 is equal to sine 3x. Okay, so when is the sine graph equal to 0? Well, it's equal to 0 when when 3x is equal to 0 or equal to 180 degrees. Sorry, we're using radians, aren't we? Beg your pardon. Pi radians, or 2 pi radians, or 3 pi radians, and so on. And so that's going to have x values of 0, pi by 3, 2 pi by 3, and pi. Now, the problem with that is some of these values are going to be maximums, like this one, and some of these are going to be minimums, like that one and that one there, right? So it's a little bit tricky. So what we could do is we could substitute x is equal to 0 into our original function. So if we do that, we would get 5 times by cos 0, which is 1, and then minus 2 would give us a y value of 3, right? Which on the graph corresponds to that stationary point there, which is a maximum value. Or alternatively, we could stick in x is equal to pi by 3. We put that into the y equation, right? So we get 5 cos 3 times by pi by 3. So cos pi is negative 1. So we get 5 times negative 1 minus 2 is negative 7. Now, if you ask me, differentiating it is the absolute crazy way to do it, right? It's unnecessarily complicated, and you've got to distinguish between having a maximum or a minimum. I think that this way here is probably the most straightforward, but there is a potential trap there. So what is the very best way to do it? The best way is basically to draw the graph, right? If you draw the graph, you've got a total understanding of what's going on, and then you can see for yourself very clearly where the minimum value is. So I know what my preference would be, and I would encourage you as students, right? Don't take the fast route. What you want to do is you always want to take the accurate route, because you want to guarantee that you get the right answer as much as anything. Okay, I hope that was helpful. Okay, question 2. It is given that y is equal to f of x, where f of x is this function here. Find the coordinates of the stationary points on the curve y equals f of x. Okay, so stationary points, right, is the place where the gradient of the graph is equal to 0. So it corresponds to a maximum or a minimum point. So let's say I've got a curve that looks something like that, right? The maximum and the minimum points will be like here, that's a local maximum, and that's here a local minimum. And what's the gradient there? Well, the gradient is going to be a horizontal line. The gradient is 0. So we refer to these as stationary points, right? Stationary points. And that's where dy dx is equal to 0. So essentially what we're being asked to do is to differentiate this function and find when it is equal to 0, okay? When the derivative is equal to 0. Okay, so how are we going to differentiate this? Well, what we've got is we've got one function multiplied by another function. So when we've got one function multiplied by another function, we have to use the product rule, right? Because what we've got is we've got the product of two functions. So essentially we can write that as this. If y is equal to a function u times by a function v, then we differentiate that by doing v times by du dx plus u times by dv dx, right? v du plus u dv. And so I've just got to identify what's what, right? So I'll call this function here u, and I'm going to call that function there v, and I just have to differentiate both of them and substitute them in. So u is equal to 2x minus 5, and v is equal to x minus 1 squared. So if I differentiate u to get u prime, 2x differentiates to 2, and negative 5 goes to 0. V, right, if I differentiate that, this is going to be a chain rule, right? Because I've got one function, x minus 1, inside the bigger function, x squared. So how do I differentiate that? Well, I differentiate the big function first. So I take that power of 2, bring it down, and subtract 1. So that's going to give me 2 bracket to the power of 1, right? So I differentiate the big thing. And then I take the small function on the inside, the x minus 1. I differentiate that, which gives me 1. And I multiply through by 1, right? So that's the chain rule, right? Chain rule is when you've got one function, x minus 1, inside a bigger function, like x squared. And then you differentiate it by doing the big function first, 2 down to the front, subtract 1 from the power, and then differentiate the small function and multiply through. All right, then. So if I substitute this in, I get y is equal to v. So that's x minus 1 squared times by du, which is 2. Plus u, which is 2x minus 5, times by dv, which is going to be 2 bracket x minus 1. Well, what do we notice? We notice that we've got a common factor. We've got x minus 1 and x minus 1, and we've also got 2 and 2. So what I can do is I can factorize those guys. So 2 bracket x minus 1. If I factorize that out of the first term, I'm left with 1x minus 1 term. And if I factorize from the second, I'm left with the 2x minus 5. So I can therefore simplify all this to be 2 bracket x minus 1 bracket. So we've got x plus 2x, which is 3x, and minus 1 minus 5, which is minus 6. So why don't I go the full way and factorize out 3 out of that? So 2 times 3 is 6, x minus 1, and then x minus 2. Right, so that's going to be the derivative. We want to find the stationary points, right? So we write stationary points when y prime equals 0. Right now, I would encourage you always to write this down, right? Don't just set this equal to 0. That's kind of lazy. And it means that you end up with confusion, I think, with tangents and normals and that kind of thing. You want to make it very clear in your mind that the only reason you're setting dy dx is equal to 0 is because you are trying to find stationary points. Okay, so 0 is equal to 6 bracket x minus 1 times by x minus 2. So that's got two solutions when x is equal to 1 and when x is equal to 2. Well, I want to read the question very carefully. We want to find the coordinates, right? So we're not just asked the x coordinate, we've also got to find the y coordinate, right? So the function is 2x minus 5 times x minus 1 squared, right? So the function is 2x minus 5 times x minus 1 all squared. So I want to find the function when x is equal to 1. So it's going to be 2 times by 1, which is 2, minus 5 is negative 3. And then 1 minus 1 is 0, isn't it? So that's going to be equal to 0. So our coordinate there would be 1, 0. And now let's substitute in 2 into the function. So we get 2 times by 2, which is 4, minus 5 is negative 1. And then 2 minus 1 is 1, all squared. And so that's going to give us a value of negative 1. And so that's going to give us 2, negative 1. Okay, so those are going to be the two values of our, or rather the two coordinates of our stationary points. Okay, then we want to think about part B. So on the axis, sketch the graph of y equals f of x, stating the intercepts with the axis. So if we just go back to the curve, right? So the curve is this guy. How are we going to get the x-intercepts? Well, we do it when y is equal to 0. And so that's going to give us 2x minus 5 is 0. So x is 5 upon 2. And x minus 1 is 0, so x is 1. So we've got x-intercepts at 5 upon 2, 2.5, and 1. Yeah, so I'm going to sort of key that in here. So I've got here, I don't know, 1, 2, 3. All right, so it's going to cut through here when x is equal to 1. It's going to cut through here at 5.2. Okay, just label that 5.2. We also want to get the y-intercept, right? How do we get the y-intercept? It's when x is equal to 0. So if x is 0, this becomes -5, and this becomes -1 squared. So -1 squared is 1, times by -5 is -5, right? So we're going to have an x-intercept here, let's say. I'll make this a bit shorter. 1, 2, 3, 4, 5. So that's -5, so it goes there. Okay, and then it'd be helpful, I think, for us to think about the stationary points, right? Because we found that in part A. So we got the two coordinates, the coordinate 1 and 0. So basically, this guy here is also a stationary point, isn't it? Right. So it's not just a x-intercept; it's a stationary point. And 2, -1. So 2, -1 will be like here. That will be a stationary point. So if I was to draw the curve. The curve's going to come up through -5 as the y-intercept. It's going to kind of come up like that. It's going to touch the x-axis there. It will come down, have a minimum at 2, -1, and it's going to come back up through there like this. Okay, so that's going to be the curve, the graph of the curve. Okay, and part C, hence find the values of k for which f of x equals k has got exactly one solution. Well, essentially what we're doing is we're finding then the intersection point between this curve and the line y is equal to k. And what does the line y equals k look like? Well, it's just a horizontal line, right, that goes through a constant value. So we can see here that in this case, the line only cuts the curve once. Whereas, for example, if we were to draw the line, let's say here, it would cut the curve at 3 points, right? 1, 2, 3. And if we were to draw the line, let's say we were to draw the line like that, it would cut it at 2 points because it would cut it here and it would just touch the curve at the minimum there. So what do we require? Basically, we require that the line is everything above the x-axis, right? So k needs to be greater than 0, right? And we also need to be lower than this minimum point, right? And the y coordinate for that minimum point is -1. So we require that k is also less than -1, right? So if you're not sure what I mean there, I'm saying that the straight line, right? The straight line, I'll draw it in blue, can't be this, right? The x-axis, it's got to be above there, okay? And moreover, it can't be, let's try to do it there. Can't be there where it kind of touches the minimum. It has to be lower than that as well, okay? So k needs to be greater than 0 and k needs to be less than -1. Okay, then question 3. The diagram shows a circle with center of O, radius of 12, and a circle with center C and radius of 5. The circles intersect at the points A and B, such that OA and OB are tangents to the circle with center C, right? So if OA is a tangent to the circle and OB is a tangent to the circle, then what that actually means is that this angle here is a right angle. So the angle between the radius of a circle and its tangent is always 90 degrees. So that's a right angle triangle there. And that is basically the key fact that you need to know. Because then what you've got is you've got a nice right angle triangle here. Okay, like that, like that, like that. And notice as well, right, that the sides of that triangle are 5 and 12. So by Pythagoras, we should also be able to get this length, which will be 13. So I'll just call it x just for the moment. But if you just think about that for a second, x squared will be equal to 12 squared plus 5 squared, which is 144 plus 25. Sorry about that, plus 25, which is 169. So therefore, x is equal to 13. Okay, so that's going to be equal to 13. So I think it's probably a good idea just to indicate that. So that's 13. Okay, now then. Show that the obtuse angle ACB, so ACB is going to be this angle here, right, is 2.35 radians, correct to 2 decimal places. Well, I think the easiest thing to do, right, is to find out this angle here, which we can do by using basic trig. and then just to double it. So let's call that angle, I don't know, let's call it phi. Okay, so we can then say that tan phi is equal to opposite, which is 12, over adjacent, which is 5. And so therefore the angle ACB, right, so that angle ACB is going to be equal to 2 lots of the tan inverse of 12.5. And so I think the best thing now is just to key that into a calculator. So 12 divided by 5. By the way, make sure your calculator is set to radians, right? So as soon as you enter this question, first thing you should do is just put your calculator in radians mode. So tan inverse answer is that times it by 2. What do I get? 2.35. Yeah, and that's what we're asked to do, isn't it? So 2.35. Okay, right. Next part B. Find the perimeter of the shaded region. Okay, well, what is the perimeter? The perimeter is going to be this length here, which is 12, plus this length here, which is 12, plus this arc length here. Now, what's the arc length going to be? Remember the two formulas for arc length, for radians, right? S is equal to r theta. So arc length is equal to the radius times by the angle in radians. And the area of the circle is equal to a half r squared theta. So we're going to have to use those two formulas. So the perimeter will be equal to 12 plus this r theta. So the r will be 5 times by the angle, which was the 2.35. So 5 times by 2.35. Okay, so let's put that into the calculator. So times by 5 plus 24, I get 35.76. Okay, so I will leave that as 35.8. Okay, and did it give us the units? Lengths are in centimeters, so this is 38.5 centimeters. Okay, part C, find the area of the shaded region. Well, I think probably the best way to do that is to find the area of this kind of kite, right? And that kite is going to be made up of two of these triangles, and then to subtract off the area of the sector there, right? And that area of the sector will be given by this formula here, right? So how do we find the area of one triangle? It's a half base times height. So let's write that down. So area of the triangle is equal to a half the base, which is 12, times by the height, which is 5. Make sure I got that right. Yeah. So it's going to be 6 times by 5, which is 30. Okay. And then the area of the sector is equal to a half r squared theta, right? So it's going to be a half times by 5 squared times by the theta, which was the 2.35. Okay, whatever that is. And so let's just key it into a calculator. So actually, I'll leave it for the moment. So what would be the total area? So the area of the shaded, will be the area of this kite, right, which is 2 lots of the triangle. So we got 2 times by 30 minus the area of the sector, which is a half, times by 5 squared, which is 25, times by the angle in radians, 2.35. Okay, so let me just do that. Okay, so times by 25, divided by 2, and I got to do 60 minus that answer, and I get 30.599. So I think that should be 30.6, and then the units will be centimeters squared. Okay, I'm just going to check my answer against the book. So 35.8 and 30.6. Let's see what we get. Uh, 35.8 and 30.6. Yeah, exactly right. Okay, so I think actually that's a relatively straightforward radians question, right? You know, they can get a lot harder, but I think so long as you see that you've got right angle triangles, that one shouldn't be too bad. Okay, so question 4, the function f is such that f of x is 4 ln 3x minus 2 for x is greater than a, where a is as small as possible. Write down the value of a. Okay, well, for a logarithm, the argument of the logarithm, which means this 3x minus 2, must be a positive number, so it must be greater than 0. So 3x minus 2 must be greater than 0 at all times. So x is greater than 2/3. So if a, which represents kind of the lowest possible value that x can be, then in this case, a must be equal to 2/3, okay? All right, so write down the range of f. Well, essentially, hopefully you know what a logarithm graph looks like, and you know that the range of values is all of the real numbers. But if you're not sure, I think I'll just draw it out for you. So here we've got the exponential graph. I'll draw first, right? So the exponential graph looks something like this. Looks like that. So we'll make that y is equal to e to the power of x, right? So that means that that's 1, and it's got an asymptote at y is equal to 0 or the x-axis. And the natural log graph is the inverse of that. That kind of looks like this. Kind of goes like that, goes like that, goes like that. And that is y is equal to the natural log of x, because e to the x and the natural log of x are inverses, right? So hopefully you can see that these guys are also going to be reflections in the line y is equal to x. What's the domain of a function? It's all of the possible x values, right? So if we look at e to the x, what would be the domain? Well, x can be anything from -infinity all the way up to +infinity. For ln x, what would be the domain? Well, we can't be negative and we can't be 0. So the domain for ln x is everything that's greater than 0. So x is greater than 0. What about the range? Well, for e to the x, the range is all the possible y values, and the y values must be everything greater than 0. So y is greater than 0. And for the natural log, the y values are can be anything. So it goes from -infinity all the way up to +infinity, or all the real numbers. Okay, so hopefully you should be familiar with what the basic log and exponential graph looks like, and then that means you'll know what the domain and the range will be. Now then, part 3, find f inverse stating its domain and range. Now I think it's important to understand what the inverse function actually is. I've done a whole video really explaining this in great detail, but I'll try to give you the very brief idea at the moment. So let's say we've got a function, we'll call it g, so we don't confuse it with what we've got in the question. And we've got its inverse, g inverse. So how does this work? Well, let's say that we take a number, let's call it 3, and we stick it into the function g, and as the output, we get 7. Okay? Now, what would the inverse function do? The inverse function should take that 7 as an input and give me back the number 3. Okay, so the whole job of the inverse function, right, is to reverse the action of the original function. So if the output of the original function was 7, the inverse function should return me back to 3, should bring me back to the original input. Okay, so inverse function reverses inputs and outputs. Well then, let's think about that a little bit more. Let's talk about domain and range. So let's say the domain of g was that x must be greater than or equal to 5. And let's say that the range of g, so that's all of the possible outputs, is everything that's, I don't know, less than -2. Okay? Well then, what would have to be the domain of g inverse, right? Now, the domain of g inverse is all of the possible inputs that can go into the inverse function. So what are the possible inputs? Well, the only inputs it can have are going to be the outputs of the original function. So if the outputs of the original function is everything that's less than -2, then the inputs to the inverse function must also be everything that's less than -2, right? And in the same way, right, what must be the outputs of the inverse function? Well, it's got to take me back to the original inputs of the original function. So the range of g inverse, the range of the inverse function, will be the same set of values as the domain of the original function. Why? Because what's the job of the inverse function? It's to take the set of the output values from the original, right, and to take me back to the set of input values for the original. right? So the domain of the inverse must be the same as the range of the original, and the range of the inverse must be the same as the domain of the original, right? Those two things must be the same. And we can see that right over here with these two graphs, right? So if I was to have the graph of e to the x and ln x, and I was to take the domain and the range, right? What was the domain of e to the x, right? It's x must be all the real numbers. What's the range of e to the x, right? Well, y is greater than 0. Okay, then. So if the natural log is the inverse of this function, then what's the domain got to be? Well, the domain's got to be the same as the range of e to the x. So x would have to be greater than 0. And what would be the range of ln x? Would it have to be the same as the domain of e to the x? So y will be all the real numbers. Okay, so that's basically the principle that we're applying, right? If two functions are inverses, then their domain and their range switch. So now if we go up to here, right? So we've got f and f inverse, right? So here we've got f, and we've got f inverse, and domain and range. Well, what was the domain of the original function f? For f, we said it was x is, what was it, greater than 2/3, I think? Yep, that was it, greater than 2/3. What was the range? Well, y could be all the real numbers. Okay, then, so what would be the domain and range of the inverse function? Well, the domain will be all the real numbers, and the range will be everything that's greater than 2/3. Why is that? Because the domain and the range, they switch. Okay, so we've answered the second part of that question. So how do we answer the first part? How do we find f inverse? Well, again, what is the inverse function, right? For the original function, right, we take in inputs, we call them x, and they give us outputs y. So what will the inverse function do? It will take outputs y and bring us back to x. So essentially, to find the inverse function, what are we going to do? We're going to take our original function, which we will call y is equal to 4 ln 3x minus 2, and we want to rearrange it to make x the subject, right? So we find x in terms of y. So if we do that, we get y upon 4 is equal to the natural log of 3x minus 2. Okay, and that means that we can then convert to exponential form. So e to the power of y upon 4 is equal to 3x minus 2. And so therefore 3x is equal to 2 plus e to the power of y upon 4. And that means that x is equal to 1/3 of 2 plus e to the power of y upon 4. And conventionally, we would then write the inverse function and say that the inputs are x. So we just take the y and we replace it with an x, right? Just basic convention. Okay, and that's going to be our 1/3, beg your pardon. And that's going to be our inverse function. Okay, all right. Okay, then, so on the axis, sketch the graphs of y is equal to f of x and f inverse of x. So f of x, right, is y is equal to 4 ln, was it 3x minus 2, I think? Yeah, 3x minus 2. And we knew that that has got an asymptote at x is equal to 2/3, and that the domain is therefore x is greater than 2/3. So we could start to draw that on, can we? So, right, 1/3, 2/3, 1, right, like that. So if that's 2/3 there, then this is going to be our asymptote. Let's try to draw that. Okay. But what also would we need to draw on? Well, it would be helpful to have the x-intercept of the long graph. Now you can do that fairly quickly, actually. The x-intercept is always going to be where the argument is equal to 1. So if you prefer, you can do that. So 3x minus 2 is equal to 1, which means 3x is equal to 3, x is equal to 1. So we're going to go through here. But if you're not sure about that, let's just go through it the long way. So an x-intercept is when y is equal to 0. So 0 is equal to 4 ln 3x minus 2. So 0 is equal to ln 3x minus 2. Then converting to exponential form, e to the 0 is equal to 3x minus 2. And e to the 0, of course, is 1, isn't it? Because anything to the power of 0 is 1. So we end up with the result that I said, which is that the argument 3x minus 2 is equal to 1. And so therefore, x is equal to 1. Okay, so that's going to be our x-intercept. So I'm just going to get rid of that now. Okay, save the space. So our curve is going to come up with the, just get rid of that because it wasn't quite right, at the asymptote of 2/3, and it's going to go up through 1, kind of like this. So let me just try to draw that. So it's like kind of like that, like that, like that, like that. Ooh. Okay, something like that. Okay, sorry, it's kind of hard to draw on a tablet, but it'd be something kind of like that. Okay, then what would the inverse of that graph be? Well, inverse, right, is a reflection in the line y is equal to x. So if I was to draw the line y is equal to x, like that, okay, then what's going to happen? Well, firstly, the asymptote is going to reflect, isn't it, right? So instead of having an asymptote at x is equal to 2/3, we're going to have an asymptote at y is equal to 2/3. So let's try to draw that on. It's like that, right? So asymptote at y is equal to 2/3. Sorry, I haven't drawn it super well, have I? Let me try to undo that. I might redraw that line again. Let me just try that. Is that a bit better? Okay, maybe that's a bit better. So my asymptote should look like that. Okay, so that's an asymptote that goes through y is equal to 2/3. And then if the x-intercept of that graph was 1, then the y-intercept will be 1 for the exponential graph, because it's reflected. So we're going to go through there. And of course, if we're reflecting in the line y equals x, we're also going to pass through this point here and this point here. So if I've got to really try to draw this carefully now. So the exponential graph is going to kind of come up through there. So I'm going to go through there. Oh my goodness, like that. Okay, not so great. Apologies for that, but it should look something like that. Okay, so something along those lines. Now, if you're wondering about how to sketch an exponential graph, so our exponential graph was, what was it? A third 2 plus e to the power x upon 4, right? So y is equal to a third 2 plus e to the power x upon 4, I think. Yeah. So how can we sketch that? Well, where are we going to get the asymptote? The asymptote happens when the exponential term, so in this case e to the x upon 4, tends towards 0. So if x becomes really, really negative, e to the power of a big negative number is almost 0. So what's going to happen to this thing here? We're going to have 2 plus 0, which is going to be 2, divided by 2, which is 1. Oh, sorry. That's a third, isn't it? Yeah, sorry, third. Yeah, silly me. That's a third there. Sorry, beg your pardon. So we're going to get 2 plus 0, which is 2, divided by 3 is 2/3. So hence the asymptote is going to be y is equal to 2/3. Do apologize about that. What about the x-intercept? The y-intercept, do beg your pardon. The y-intercept is when x is equal to 0. So what's going to happen there? Well, if x is equal to 0, e to the power of 0 is 1. So we're going to get 2 plus 1 is 3, divided by 3 is 1. So we're going to get a y-intercept there. So hopefully you can see like how we can sketch a logarithmic graph and an exponential graph. We've got to know where the asymptote is, and we've got to be able to calculate where the x and y-intercepts are, but also we can use our knowledge of the fact that these two graphs are inverses, and therefore if they're inverses, they reflect in the line y equals x. Okay, I hope that was helpful. Okay, part B of this question, given that g of x is equal to this, solve the equation g of x is equal to 9. What does g of x mean? It means we take the function g and we stick it inside the function g. All right, so it's a composite function. So essentially everywhere here where we've got an x, we're going to replace it with the entire function g. So what would that look like? Well, we can have 2. Now, instead of x, we need to now have this whole thing as well. So 2x plus 1 to the power of a half plus 4. Okay, like that. Plus 1 to the power of a half plus 4. So I hope you can see what I've done there, right? Instead of the x, I've replaced the x with this entire function here of g. So how can we solve this? Well, we're told this is equal to 9, aren't we? So, so 9 is going to be equal to this whole thing, right? So 2 bracket 2x plus 1 to the power of a half plus 4, close bracket, plus 1, close bracket, to the power of a half plus 4. So we can subtract 4 from both sides. So that becomes 5 is equal to this whole bracket thing to the power of a half. We can then square both sides, which will give us 25, right? So 25 will be equal to the thing that was inside the bracket. So 2 bracket 2x plus 1 to the power of a half plus 4 plus 1, like that. So we can then subtract 1, which will give us 24, and divide by 2, which will give us 12. So 12 will be equal to 2x plus 1 to the power of a half plus 4. And we can subtract 4. That will give us 8. So 8 is equal to 2x plus 1 to the power of a half. We can then square both sides, which will give us 64 is equal to 2x plus 1. So 2x will be equal to 63. So x will be equal to 63 upon 2. And I'm just going to check the mark scheme, see if that is correct. Yeah, 63 upon 2, which is 31.5. Now, I think that that is quite a ridiculous way of doing it, right? It's quite long, quite complicated. So can I suggest to you an alternative way? And it's really basically understanding what composite functions are. So what is a composite function? Let's say we've got a variable x, okay, and we put that into the function g. And then what do? We take the output of that and we stick it into the function g, okay? And then that's going to give us our output, which is y. So this whole thing here, right, that whole thing is what we refer to when we say g of x, okay? Because that's what we're doing with the composite function. Now, how could we solve to get back? Well, we could invert it, couldn't we? And what's that going to involve? Well, we could go from y back to here. And to do that, we would have to go through the inverse function of g. And then once we're there, we could go back again, right? Using the inverse function of g again, right? So basically, if the path of our variable x is to go through g and then through g again, then how do we reverse that? Well, we go through g inverse and then we go through g inverse again. So I think that's basically the best way to think about it. So if we've got our function g, so let's write it as y is equal to, what on earth was it? It was 2x plus 1 to the power of a half plus 4, okay? So 2x plus 1 to the power of a half plus 4, okay? And of course, that's the same thing, isn't it, as the square root of 2x plus 1 plus 4. So how can I invert that? I'm going to get y minus 4 is equal to the square root of 2x plus 1. So y minus 4 all squared is equal to 2x plus 1. So x is going to be equal to y minus 4 all squared minus 1 divided through by 2. Okay, or if we prefer, like times by half. So what does that mean? It means that we can write our inverse function, doesn't it, as g inverse of x is equal to a half of x minus 4 all squared minus 1. So what are we going to do? We are told in the question, isn't it, that g of x is equal to 9. So the outcome is we get 9 here, right? So like y is equal to 9. So what I need to do, I need to stick 9 into the inverse function, don't I? And then once I've done it, I need to stick it into the inverse function again. So that's exactly what I'm going to do. So I'm going to find g inverse of 9. So that's equal to a half of 9 minus 4 is 5, isn't it? Squared is 25, and then 25 minus 1 is 24. And so half of that is equal to 12. Okay, so then what I want to do is want to put 12 into the inverse function again. So g inverse of 12 is a half of 12 minus 4, which is 8 squared minus 1. 8 squared is 64, minus 1 is 63, a half is 63 upon 2. Okay, so if you can understand what I've just done there, right? I've said that if we apply the inverse function once, we get this value here, which is 12. And if we apply it again, we're going to get 63 upon 2. Right? So essentially what I'm saying is if we understand how composite functions, what they actually mean and how inverse functions work, we can think about this problem in a different way. And in my view, I think it is actually a simpler way. It's a way that's going to have less problems. It's to say that we've got this value 63 upon 2. If we put it through the function g, we'll get 12. If we put it through g again, we'd get 9. And what that means is that if we were to put 9 through the inverse function, we would get to 12. And if we put 12 in the inverse function again, we get 63 upon 2. So I mean, you may disagree with me. You may think that's harder. But I think in general, it's a good idea to have an understanding of like what these things actually mean, what they represent, and how we can manipulate them rather than just being able to do the algebra. Okay, I think that the more ways you can understand something, the more ways you can do something, the better it is for you. Okay, so I hope that that was helpful. If you're finding this kind of material, by the way, to be good, please like and subscribe and share with your friends. Okay, question 5. Show that 1 plus cot squared theta divided by cot squared theta is equal to sec squared theta. Okay, to do this, we basically got to use the trig identities that we're given in the front of the exam paper. But first of all, what I'm going to do is I'm going to split up the left-hand side. So I'm going to get 1 over cot squared theta plus cot squared theta over cot squared theta. Now, what is 1 divided by cot squared theta? Well, we've got to understand what cot represents. And to do that, we're going to look at the third letter. 1, 2, 3, t. So that means that cot theta is equal to 1 divided by tan theta, right? So the third letter always tells you, for example, if we had sec, the third letter is c, so that would be 1 divided by cos. If we had cosec, the third letter is s, so that would be 1 divided by sine. So we know that cot is 1 divided by tan, so that means 1 divided by cot is equal to tan, right? Because we can basically invert it like that. So therefore, 1 upon cot squared theta is tan squared theta. And then cot squared divided by cot squared is just equal to 1. So we've now got tan squared plus 1. And if we look in the front of our exam paper at the identities, we're actually told that tan squared theta plus 1 is equal to sec squared theta. Okay, so if we do that, we've already reached our answer. Okay, so let's go to part B. Write down the derivative of tan theta with respect to theta. Okay, well, hopefully you should know that if y is equal to tan theta, then that means that the derivative y prime will be equal to sec squared theta. But let's say that you don't know that. How could you find it out? Well, tan theta, right, is sine theta over cos theta. And so what we've got is we've got one function divided by another function. And so therefore we can use the quotient rule. Okay, now what is the quotient rule? The quotient rule is v du minus u dv over v squared. So if I was to substitute this in, right, my v is cos theta. If I differentiate my u, which is sine theta, I also get cos theta. And my u is sine theta. And if I differentiate cos theta, I get negative sine theta. And this is all divided through by v squared, where v is cos theta. So I divide through there by cos theta, so I get cos squared theta. Now, the key thing to recognize is that this is cos squared, and this is negative sine theta times negative sine theta, which is plus sine squared theta. So we get cos squared plus sine squared, and cos squared plus sine squared is 1. So we get 1 over cos squared theta, and that's going to be the same thing as sec squared theta. Okay, so if you were never sure about that, or you wanted a way of trying to prove it to yourself, that's the way we do it. So The key thing, though, is just the end result, that y prime is equal to sec squared theta. Okay, so now using part A and part B, find the exact value of this integral. Okay, well, essentially what we've got to do is we've got to really understand what integration is, right? So let's say that we've got a function, let's call it big F of x, and we differentiate this function, right? So we differentiate, and as a result of that, we get little f of x. Well, what that therefore means is that if we were to integrate little f of x, we would get back to big F. Okay, so essentially, if we know how one function differentiates, we could reverse that to know how it integrates. So for example, let's say we've got sine x, and we differentiate it and we get cos x, right? So if we know that sine differentiates to give cos, that now means that we know that if we integrate cos, we're going to get back up to sine. Okay, so that's the key idea here. Okay, so how are we going to use this? Well, the first thing is, right, is that we can replace this expression here, the 1 plus cot squared theta over cot squared theta, with sec squared theta from part A. So we can start by saying we are doing the integral of sec squared theta minus sine theta d theta. Okay, so this is the integral that we're doing. If we were to integrate sec squared theta, what will we get? Well, we will get tan theta, won't we? Because if we differentiate tan theta, we get sec squared theta. That's what we learned in part B, which means that if we were reversing that, if we integrated sec squared, we would get tan. So this thing becomes tan theta. And then lastly, if I was to integrate negative sine theta, I would get positive cos. And again, why is that the case? Because if I was to differentiate cos, I would get negative sine, right? So essentially, what I'm doing is I'm reversing my differentiation. Okay, so now we just got to substitute in the bounds, right? So I've got to substitute in pi by 3. So I'm going to get tan of pi by 3 plus cos of pi by 3 minus tan of 0 plus cos of 0. Okay, so we need to know these critical values, right, for pi by 3 and for 0. So let's assume that you don't have a calculator. How can we do that? We need to remember this equilateral triangle here. Right, so this is an equilateral triangle. If it's an equilateral triangle, then this angle here is going to be 60 degrees or pi by 3. And let's take that equilateral triangle and let's cut it in half down the middle such that this is 90 degrees there. And if that's the case, then this angle is going to be a half of pi by 3, which is pi by 6. Okay, so now let's try to think of what lengths we could use. Well, if I choose the length to be 2, then this length here, right, is going to be 1, right, because it's a half of the 2. And so then we could use the Pythagoras to find this height. And that means that, we'll call it h, right? That means that 1 squared plus h squared is going to be equal to 2 squared. So h squared will be equal to 3, so h will be equal to root 3, right? So this length here is equal to root 3. And I've deleted the other side of the triangle because it's no longer relevant. Okay, so I've got this triangle here. And so therefore I can find out what tan pi by 3 is, because tan is opposite over adjacent. So tan pi by 3 is root 3 divided by 1. So I end up with root 3. Cos pi by 3 is adjacent over hypotenuse. So adjacent is 1, hypotenuse is 2. So we end up with 1 upon 2. And what's tan 0? Well, tan 0 is 0. And what is cos 0? Cos 0 is positive 1. So we end up with root 3 plus a half minus 1, which is minus a half. Okay, and so that's my answer for this part. Let me just check the mark scheme, see if I've got that right. So root 3 minus a half, exactly right. Okay, question 6. This is a binomial expansion question. So find in descending powers of x, which means the powers of x have got to get smaller, the first three terms in this expansion here. Simplify each term as far as possible. Okay, well, hopefully this is fairly straightforward. So if you're practicing these exams, I think knowing the basic way to do an expansion should be reasonably okay. But let me just go through how I do it. So I take the first term, which is x, right? And that term, the powers are going to decrease. So we're going to have x to the power 10, x to the power 9, and x to the power 8, and so on and so on. And then the second term, which is 2 upon x squared, the powers are going to increase. So we get 2 upon x squared to the power 0, and 2 upon x squared to the power 1, and 2 upon x squared to the power 2, and so on and so on. And what should you notice? That these powers always add up to 10, right? So 10 plus 0 is 10, 9 plus 1 is 10, 8 plus 2 is 10. Then what's the last thing that we've got? Well, we've got to have the coefficients. So the coefficients will be 10c0, 10c1, 10c2, and so on and so forth. Okay, and then plus dot, 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 because it carries on. All right, so now we just got to simplify this. So 10c0 is 1, x to the power 10, and 2 upon x squared to the power 0 is 1, because anything to the power of 0 is 1. 10c1 is just 10, x to the power 9, and then 2 upon x squared to the power 1 is just 2 upon x squared. Okay, then 10c2, what's that? Well, let's assume we don't have a calculator. The formula for that will be 10 factorial over 2 factorial 8 factorial times by x to the power 8. And then 2 upon x squared, all squared, is 4 upon x to the power 4 plus dot, 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 dot. All right, now then, let's simplify this. So we get 1 times x to the power 10 times by 1, which is x to the power 10. Okay, well, we can cancel off x squared from the second term. So that will become x to the power 7, or if you prefer, it's like we're subtracting the powers, right? So 9 minus 2 is 7. 10 times by 2 is 20, so this is going to be plus 20, x to the power of 7. How can I simplify this term here? Well, 10 factorial, right, divided by 8 factorial is just going to leave us with 10 times 9. Why is that? Well, because 10 factorial is 10 times 9 times 8 times 7 times 6 times 5, blah, 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 blah. And we're dividing it by 8 times 7 times 6 times 5, da, 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 which means everything below, which is 8 and below, is going to cancel off. So we're just left with 10 times by 9. And here, 2 factorial is just 2 times by, okay, what's going to happen to the x term? Well, x to the power 4 is going to cancel off. So we're left with x to the power 4 on the numerator and times by 4. So now hopefully we can simplify this. I'll divide through by 2, right? So that becomes 2. So I'm going to end up with x to the power 10 plus 20 x to the power 7. I have got 2 times by 9, which is 18, times by 10 is 180. So I've got 180 x to the power 4 plus dot, 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 what is left over. Now let me just check that I have got that right. Yep, that is correct. Okay, so let's go to the next part. Find the term independent of x in this expansion. What does independent of x mean? It means that there is no x value. Okay, so it's just going to be a constant term. So let's try to examine how that's going to work. So we've got 4x squared plus 1 upon 2x squared to the power of 8. What is every single term in this expansion going to look like? It's going to be a 4x squared to some power times by a 1 upon 2x squared to another power, and then with a coefficient of 8c something. Okay, now basically we've got to choose the powers that go here and here in such a way that the x's are going to cancel off. Now, these two powers must add up to be 8. So I've got to choose like either 0 and 8, or 1 and 7, or 2 and 6, or 3 and 5, or 4 and 4, or any of the others, so that these x's cancel off. Now, how can I do that? Well, if I chose that to be 4 and that to be 4, then I'm going to end up with an x to the power of 8 and divided by an x to the power of 8. So the x's will cancel off. So that's exactly what I want. And then this number here will be 4, because the number that goes here can either be this power or that power. Well, in this case, both of those are the same. So now I just got to simplify. Again, let's assume I don't have a calculator. 8c4 is 8 factorial over 4 factorial times by 4 factorial using the formula. We've then got 4 to the power of 4 times by x squared to the power of 4, which is x to the power of 8. And this is over 1 over 2 to the power of 4 times by x to the power of 8. So first things first is that those x to the power of 8 terms disappear. Okay, let's try to simplify this again, assuming we don't have a calculator. So we've got 8 times 7 times 6 times 5 divided by 4 times 3 times 2 times 1, right? Because the other 4, 3, 2, 1 terms cancel off because that's 4 factorial. We've got 4 to the power of 4. Well, I'll rewrite that, I think. I will call that 2 to the power of 2 to the power of 4. And then times by 1 over 2 to the power of 4. So how can we now simplify this? Well, look, 8 is the same thing as 4 times 2, right? So I can cancel off that, and I can cancel off a 3. So divide the 6 by 3 gives me 2. So let's try to simplify this. I've now got 7 times by 2 times by 5 times by 2 to the power of 8, right? Because I multiply these two powers together, and then divided through by 2 to the power of 4. And of course, I can then simplify this by subtracting the power. So 8 minus 4 is 4. So this becomes, right, 7 times by 2 times by 5 times by 2 to the power of 4. Okay, well, there's a couple of ways you could do that now. 2 to the power of 4 is 16. And I could do 16 times by 7 and then times it by 10 because, 2 times 5 is 10. So I don't know, let's do that. 16 times by 7. Okay, so 7 times by 6 is 42. And then 7 times by 10 is going to be 70, isn't it? So if I then add those up, I'm going to get 2. Okay, so 112. Yeah. And so I've then got to have 112 times by the remaining 10, which is 1120. Okay, so I've done that, a little bit extra there, right? Because I know that you're not going to have calculators moving forward. So I want to show you, some of the tricks that can enable you to do that more effectively. And we've done that there. And that is the right answer. Okay. Okay, then question 7 here. It is given that y is equal to this thing for a domain of x is greater than 1 upon root 3. When x is equal to 1, y is increasing at a rate of h units per second. Find in terms of h the corresponding rate of change of x, giving your answer in exact form. Okay, so we need to really read and interpret what's going on here, right? Y is increasing at the rate of h units per second. So what does this actually refer to, right? This is the rate of change of y with respect to time, right? Because it's the change of y per second. And we're told that this is equal to h. Now, what we're being asked to find is the corresponding rate of change of x, which is we're being asked to find dx dt. All right, so that's what the question is asking. Now, how can we do that? Well, basically, we can use the chain rule because dy dt will be equal to dy dx times by dx dt. And why is that? Well, because we can treat these like fractions, even though they're not fractions, we can kind of pretend that they are. And if we were to cancel off the dx, then on the right-hand side, we've got dy dt. So essentially, the question is really, can we differentiate this function with respect to x? Because we need to find dy dx. So what is our function? Our function is ln 3x squared minus 1. So y is equal to ln 3x squared minus 1 divided by x plus 2. Okay, so if we want to differentiate this, right, we've got to use the quotient rule because the quotient rule is when we've got one function divided by another function. So let's just recap what the quotient rule is. It is v u prime minus u v prime all over v squared, right? So v du minus u dv over v squared. The classic error is to get these two things the wrong way round and get the negative sign wrong, right? So you need to make sure you got it in the right order. Okay, so let's be nice and patient. Let's make u equal to the ln 3x squared minus 1. And the v is the function on the bottom, the x plus 2. So we need to differentiate both of these. So u prime. So if I differentiate the natural log, the thing inside the natural log goes on the denominator. So 3x squared minus 1. I then differentiate that thing, which will give me 6x, and I stick it on the numerator, right? So that's how we differentiate a natural log. For x plus 2, if I differentiate it, I'm just going to get 1 because 1x differentiates to give 1 and 2 is a constant, so differentiates to give 0. So now I've just got to substitute it in to my quotient rule. Y prime is v, which is x plus 2, times by du, which is 6x over 3x squared minus 1, minus u, which is ln 3x squared minus 1 times by dv, which is 1, all over v squared, which is x plus 2 all squared. And we're told that we're interested in the case when x is equal to 1. So now we can just substitute straight into there, right? So when x is equal to 1, y prime is going to be equal to 1 plus 2, which is 3, times by 6 times by 1, which is 6, over 3 times 1 squared, which is 3, minus 1, which is 2, minus the natural log of 3 times by 1 squared, which is 3, minus 1, which is 2, times by 1, so no change, all divided through by 1 plus 2, which is 3, and then 3 squared is 9. Okay, so I think I've got that all right. Okay, we can simplify this, I think, a little bit. All right, so 3 times by 6 is 18, divided by 2 is 9. So we've got 9 minus ln 2 all over 9, okay, which is 1 minus a ninth of ln 2. Okay, then. So now what were we asked to find? We were asked to find dx dt, weren't we? So returning back to the original idea, right, dy dt is equal to dy dx times by dx dt. So our dy dt was h, and our dy dx, right? Well, I'll write it in the form 9 minus ln 2 upon 9 times by dx dt. So what's dx dt going to be? Just got to rearrange it, right? So dx dt will be equal to 9 times by h over 9 minus ln 2. Okay, so I think that should be our answer in exact form as requested. Let me just check the answer. 9h over 9 minus ln 2 is the right answer. Okay. All right, then question 8. The tangent to this curve here at the point when x is equal to 2 meets the x-axis of the point x and the y-axis of the point y. Find the coordinates of the midpoint of xy, giving your answer in exact form. Okay, well, basically we just want to find the equation of the tangent to the curve, isn't it, right? And so how do I find the equation of any line? I need two things, right? So the first thing I need is the coordinate point on the line. And the second thing I need is the gradient of the line. Because if I've got those two things, I can substitute it into the formula y minus y1 is equal to mx minus x1, right? So I need a coordinate point and I need a gradient. So how am I going to get the coordinate point? Well, that should be fairly easy. I've just got to substitute x is equal to 2 into here. So let's do that first. So when x is equal to 2, y is going to be equal to e to the power of 2. 2 times by 2, which is 4, plus 5, which is 9 to the power of a half. What's 9 to the power of a half? It's the same thing as the square root of 9, which is equal to 3. So we get 3e squared, right? So my coordinate, so I'll call it point P, is 2, 3e squared, right? So we've answered the first part. We've got the coordinate point. So now we want to find the gradient. How do I find the gradient? Well, I need to differentiate. So the question is, how can I differentiate this? Well, I've got one function times by another function. So if I've got one function times by another function, I need to use the product rule because I've got the product of two functions, right? So what is the product rule? Product rule, y prime, is v du plus u dv, right? So vu prime plus uv prime. So in this case, what's my u? My u is e to the x. And what's my v? My v was the 2x plus 5 to the power of a half. Okay, so let's differentiate this. If I differentiate u, right, differentiate e to the x, I get e to the x, because e to the x differentiates to give itself. If I differentiate v, how do I do that? This is a chain rule. So I take the big function there, which is the bracket to the power of a half. I bring the half down to the front, and I subtract 1. So it's going to give me a half bracket to the power of negative a half. And then what do? I differentiate the function on the inside, 2x plus 5. And if I differentiate that, I get 2, and I multiply through by 2. Okay, so the key thing to differentiating the chain rule, right, which is one function inside another function, so in this case, 2x plus 5 inside x to the power of a half, is I differentiate the big thing first, so half down to the front, reduce the half by 1, then I differentiate the little function on the inside and multiply through. And of course, in this case, the half and the 2 just cancel. So now if I substitute into the equation for the product rule, I'm going to get v, which is 2x plus 5 to the power of a half, times by du, which is e to the x, plus u, which is e to the x, times by dv, which is 2x plus 5 to the power of minus a half. And we're interested in this when x is equal to 2, is it? Yeah, x is equal to 2. So when x is equal to 2, y prime is equal to 2 times 2, which is 4, plus 5 is 9 to the power of a half, e to the power of 2, plus e to the power of 2, 2x plus 5, which again is 9 to the power of minus a half. Okay, so what's 9 to the power of a half? It's the same thing as the square root of 9, which is 3. So we've got 3 squared. And what is e to the power minus a half? Well, the negative means 1 divided by, right? So that literally means 1 over 9 to the power of a half. And 9 to the power of a half, right, is just 3. So this is 3 there. So if I factorize out e squared, right, then I'm going to get 3 plus a third. And what's 3 plus a third? Well, 3 can be written as 9 thirds, right? So we've got 9 thirds plus 1 third is 10 thirds. This is 10 thirds e squared, right? So now what I've got is I have got my gradient as well. So I've got the point, I've got the gradient, so I can now substitute in. So I've got y minus y1. So I've got y minus, what was y1? 3e squared is equal to the gradient m, which was 10 upon 3e squared, x minus x1, and x1 was 2. Okay, so we got the equation of the tangent now. So what do we need after this? Well, we need to find the x-intercept, which is x, and the y-intercept, which is y. Well, how do we do that? The x-intercept is when y is equal to 0, isn't it? So 0 minus 3e squared is equal to 10 upon 3e squared x minus 2. So I can divide through by e squared. First of all, cancel. And I'll times both sides by 3 and divide by 10. So that's going to be minus 9 upon 10 is equal to x minus 2. So x is equal to 2 minus 9 upon 10. Because I add 2 to both sides. So 2 can be written as 20 upon 10. So 20 upon 10 minus 9 upon 10 is 11 upon 10, right? So the coordinate of x is 11 upon 10, comma 0. And what about the y-intercept? The y-intercept is when x is equal to 0. So substitute in x is 0. So we're going to get y minus 3e squared. So y minus 3e squared is equal to m, 10 upon 3e squared, 10 upon 3e squared, bracket, x, which is 0, minus 2. So minus 2. Okay, so let's now simplify all that. So we've got y minus 3e squared is equal to 20 upon 3, sorry, negative 20 upon 3e squared. I think that's right. And so we've got to add the 3e squared to both sides. So we're going to get 3e squared minus 20 upon 3e squared. So 3 can be written as 9 upon 3. So we've got 9 upon 3 minus 20 upon 3, which is minus 11 upon 3 e squared, right? So I think that my y value is 0, negative 11 upon 3 e squared. Okay, so now what I want to do is I want to find the midpoint of these two. Well, how do I find the midpoint? Midpoint is I add up the two x coordinates and divide by 2. So 11 upon 10 plus 0 over 2. And add up the two y coordinates. So 0 plus minus 11 upon 3e squared. And I divide by 2. So that's going to give me 11 upon 20 and negative 11 upon 6e squared. Okay, so that should be our answer. And I'm just going to check that out against the mark scheme. So I think it's possible I've just made a small slip. Be quite plausible. No, I haven't. Okay, oh, I was quite lucky there. So that's the right answer. All right, question 9. Sorry, I've had to shrink this so I can fit it on the page, so it may not be totally clear, but the diagram shows part of the curve y is equal to 4 upon 2x minus 1, so that's that curve there. The straight line, 2y is equal to 6x plus 1, so that's that line there. Find the area of the shaded region, which is this thing here in the form ln a plus b, where a is an integer and b is a rational number. Okay, well, as I say, when we look at this, we always think it's an integration question, which is true. But before we think of it as integration, I think it's better to think of it as how do we find the area? So if I want to find that area, what could I use? Well, I could split it up, right? I could say I want to find the area underneath the curve, which would be like this whole region here. And then what I want to do is I want to subtract off the area of this trapezium there. Right, so I've got a little trapezium there. So let me highlight that in blue. So like that guy there. So the first thing I want to do actually is just want to find the area of the trapezium. And how am I going to find the area of the trapezium? Well, I'm going to need to know the height of both of these sides, and I'm going to need to know the width of that. So that's all going to hinge upon me finding the intersection point here. So that's going to be my first job to do, is to find the intersection point. So I'm going to do that with simultaneous equations, where I'm going to substitute this equation into that one. So if I write that down, I'm going to get 2 lots of 4 upon 2x plus 1. Yep, is equal to 6x plus 1. So I'm going to multiply through, right? So I'm going to get 2 times by 4 is equal to 6x plus 1 times by 2x plus 1, which is going to expand to give me 12x plus 6x plus 2x, which is 8x plus 1. So it's going to be equal to 8. So 0 is equal to 12x plus 8x minus 7. Oh, that's not a nice one, is it? So I'm going to have to factorize that. Okay. It could factorize to give me 12x and 1x, or 6x and 2x, or 4x and 3x. And the only two numbers that multiply to give 7 will be 7 and 1. So that's going to help us a little bit. Let's try 6x and 2x. Is there any way that that's going to work? So if I put 7 here, that's going to be 42, isn't it? So that's clearly not right. If I put the 7 here, that's going to be 14. Oh yeah, that would work, wouldn't it? So if I had plus 7 there, and then minus 1, so let me just double check that. So 6x times 2x is 12x. The 7 times by 2x is going to be 14x, minus 6x will give me 8x, and 7 times by negative 1 is negative 7. So that works. That's great. Of course, if you can't do that, you could always use the quadratic formula as well. That would give you the answer. So x is equal to negative 7 upon 6, or x is equal to 1 upon 2. Now, which of those answers are we interested in? We're interested in that one because it's the positive answer, right? This guy is not relevant for us. So we now know that this coordinate here is a half, okay? So if x is equal to half, we should be able to find the y coordinate there, which we can do by substituting into here, I guess. So substitute Sorry about that. So substitute into one of the equations. So I don't know, 2y is equal to 6 times a half, which is 3 plus 1. So 3 plus 1 is 4. So y is going to be equal to 2, isn't it? Right. So the y coordinate there is going to be 2. Okay, which means that this length here, that height is 2. This x coordinate is 0, isn't it? So we could find out this length now by substituting x is 0 into the line. So if I substitute x is 0 into here, I get 2y is equal to 1. So that means y is equal to a half. So this height here is equal to a half, right? So we've now got enough, I think, to find the area of the trapezium. So let me work on doing that. So area of the trapezium is equal to a half of, bracket, a half plus 2 times by the base, which is a half. Okay, and oh, I don't know, what's a half plus 2? 2.5, 5.2. So we got a half times by 5.2 times by 5.2, oh, times by 1 upon 2, do beg your pardon, silly me, times by 1 upon 2, which is 5.8. Okay, so we got the area of the trapezium. So now what we want to do is we want to find the area underneath the curve. Okay, so that's going to be integrating 4 over 2x plus 1 dx between 0 and a half, right? Because if we go to the diagram, right, to find the area underneath that curve, right, which is going to be that whole great big region there, we're integrating it from here all the way up to there. Okay, now, so if we were to integrate this guy, what are we going to get? Well, we've got 4. 1 over 2x plus 1 integrates to give the natural log of 2x plus 1. And then we've got to take the coefficient of x, which is 2, and divide by 2. So we've got that there. And we're integrating that between a half and 0. So that's the same thing as 2, the natural log of 2x plus 1, integrated between a half and 0. Or 0 and a half, I should probably say. So if I substitute in the top bound, I'm going to get 2. The natural log of 2 times a half is 1, plus 1 is 2, so it's 2 ln 2, minus, if I substitute in the lower bound, I get 2 ln, 2 times by 0 is 0, plus 1 is 1, and ln 1 is equal to 0. So that guy disappears. So we've got 2 ln 2. 2 ln 2. So what's going to be the total area? So the total is going to be the area under the curve, right? So 2 ln 2 minus the area of the trapezium, which is 5.8. So that should be our answer, but let's just double check because it says we want to write it as ln a plus b, where a is an integer. So I'm just going to use a logarithm rule here. This is going to be ln 2 squared minus 5.8. So that's ln 4 minus 5 upon 8, right? So what have I just done there? I've taken the coefficient of 2, I've brought it up as a power. So let me check the answer. Ln 4 minus 5/8. And that is the correct answer. Okay, so I hope that was helpful. All right, question 10. This is an arithmetic geometric progression style question. So the first 3 terms of an arithmetic progression are 2 tan 2x, 5 tan 2x, 8 tan 2x. Find the values of x where x is between 180, negative 180 and 180, for which the sum to 30 terms is this thing here. Okay, if it's an arithmetic progression, it means we're adding each time. So there is a common difference. What's the common difference? Well, if I go from 2 tan 2x to 5 tan 2x, that means I've added 3 tan 2x, right? So the most important thing is to state that the common difference here is 3 tan 2x. And the first term a is equal to 2 tan 2x, okay? So the sum of the first 30 terms, well, if we've got an arithmetic progression, the sum of the first n terms is given by n upon 2, big bracket, 2a plus n minus 1d, right? So in this case, if we're being asked to find the sum of the first 30 terms, that's going to be 30 upon 2, bracket 2a plus 29d. Okay, so we just substitute in our value for a and d, right? So 30 upon 2 is 15. So we got 2 times by a. So we got 2 times by 2 tan 2x. That's a lot of 2's, isn't it? So 4 tan 2x plus 29 times by d, with d is 3 tan 2x. So what's 29 times by 3? Well, 30 times by 3 is 90, minus 3 is going to be 87. So it's going to be plus 87 tan 2x. Okay. All right. So that's looking okay so far. So let's combine that. So I've therefore got 15 times by 4 plus 87 is 91 tan 2x. Now we're told that this should be equal to 455 root 3. So 455 root 3. Okay, so that is begging, isn't it, to be factorized somehow. I will try to factorize that by 5 first. So 450, right, divided by 5 is going to be 90, right? Because 45 divided by 5 is 9. And so 455 will factorize to give 91. So that's going to be 91 root 3 times by 3 times by 91 tan 2x. So if you're just wondering what I've done there, right, I've divided both sides by 5. Okay, so I've divided by 5. Now that's nice, isn't it? Because we've got a 91 has appeared, and that can cancel. So in other words, what we're left with is root 3 is equal to 3 tan 2x, which is the same thing as trying to say tan 2x is equal to root 3 upon 3, or which is the same thing as 1 upon root 3. Now, again, that's a critical angle. So if you remember earlier on in this video, I did go through that, but essentially you need to memorize this particular triangle. This is a right angle triangle, which comes from the equilateral triangle. This length is 2, that length is 1, that length is root 3. This angle is 60 degrees, and this angle is 30 degrees. So what does this tell us? It tells us that tan of 60 degrees is opposite over adjacent. So root 3 divided by 1, which is root 3. And tan 30 degrees is equal to, so that's 30, opposite over adjacent. So 1 upon root 3. So if tan 2x, right, is equal to 1 upon root 3, then what that means is that 2x will be equal to 30 degrees. And of course, the tan wave, right, it repeats with a period of 180. So I can take this 30 degrees, right, and I can add multiples of 180. So add and subtract k lots of 180. So if I was to divide all this by 2, then x is equal to 15 degrees plus or minus multiples of 90 degrees. And so therefore, if I was to do that, so I've got 15, right? If I add 90, oh, that's going to be 105 degrees. If I add another 90, that would be 195, which is too big. And then if I do 15 minus 90, that's going to be minus 75. And if I subtract another 90, that's minus 165, I think. Minus 165. So I think that should be all of my answers that are within the domain. So I am going to check that. Negative 165, negative 75, 15, and 105. Those are all the correct answers. Okay. All right. So I did that a little bit fast there with the trig. If you really weren't sure, then what you could do is you could draw the graph of tan x. I do that on other videos, so you could always check that out. But I think it would be a little bit overkill here. It should be just sufficient to realize that the tan graph repeats every 180. So I can take my basic solution of 30 degrees and just add 180 or subtract 180 multiple times. Okay, so I hope that was helpful. Okay, so this is the last question of the paper, and I think it's really quite challenging. Let's try to go through it. So the first 3 terms of a geometric progression are these things here. I want to find the values of theta for which this geometric progression has a sum to infinity. Okay then, let's try to think it through. Firstly, a geometric progression is one in which we're multiplying to get to the next term, right? So we take this term, we multiply by a common ratio to get to the second term, multiplied by the same common ratio to get to the third term, and so on and so on. So how can I find the common ratio? Well, I could do the second term divided by the first, or I could do the third term divided by the second. So I'll take the second term, 20 cos to the 4 theta minus pi by 2. And I'm going to divide it by the first, which is 5 cos squared theta minus pi by 2. And if I do that, right, 20 divided by 5 is 4. Cos to the power 4 divided by cos squared is cos squared. So that's our common ratio there. Okay, then. Now, we're asked to find the values of theta for which this geometric progression has got a sum to infinity. Now, we need to understand this idea of sum to infinity. So let's just have a think about that. Let's say that I have got two different geometric progressions, which I'm adding up. So this will be the first geometric progression. So 1 plus 2 plus 4 plus 8 plus 16, and so on and so on. And the second geometric progression will be this one. 1 plus a third plus a ninth plus 1 upon 27, and so on and so on. Now, the thing is, right, the first of these is going to keep growing and growing and growing and growing, right? Because every single term is getting bigger and bigger and bigger and bigger. So the sum, if I kept on continuing this progression forever and ever and ever, is going to be infinite, right? It's just going to keep growing. And we refer to this as a divergent progression, right? When something diverges, it means it kind of gets further and further and further apart, right? So these terms are getting bigger and bigger and bigger and bigger. So the whole sum is going to get bigger and bigger and bigger as well. Now, if we contrast it to the second of these progressions, each term here is getting smaller and smaller and smaller and smaller. So if the series carried on forever and ever, right? If it was an infinite series, kept on going and going and going, then this is going to converge. Because if we think about it, the terms over here are going to get so small that they're basically going to be equal to 0. And so then if we keep adding them to our progression, well, if we add 0, right, the summation doesn't change. You think about it, if I've got 5 and I add 0, it's just still going to be 5. So this particular summation reaches a limit, right? A limit reaches a fixed value, and we refer to that as the sum to infinity. Right, so when we talk about the sum to infinity, what we really mean is, imagine we've got a geometric progression which goes on forever and ever and ever and ever, but when we add up all the terms, we end up with basically a fixed number because the progression is not expanding. It's not getting bigger and bigger and bigger. It's getting smaller and smaller and smaller and smaller. So as I keep doing the summation, I'm basically adding 0 and 0 and 0. Okay? Now, what is the condition for this? Right? The condition has got to be that the common ratio needs to be a fraction, needs to be less than 1. And we can sort of extend that idea a little bit as well. It can actually be between -1 and 1, right? So if convergent, in other words, if we've got a sum to infinity, then the common ratio needs to be between -1 and +1. And if you're not sure about the negative there, just for a second, let's just imagine that the common ratio in this case was not a third, but it was -1/3. Well, then what would we get? We would get 1 minus a third plus a ninth minus a 27th plus 1 upon 81 and so on. Now, even though we've got plus minus plus there, it doesn't matter because what's going to happen is eventually the terms are so small that they're 0, right? So the summation will still reach a fixed limit. Okay, so that's what's going on there. So essentially, what we're really being asked to do is we're being asked to find when this common ratio is between -1 and +1. So that's what we're going to do. So we want to find out when 4 cos squared theta minus pi by 2 is between 1 and -1. Okay, so we can then divide this through by 4. So we can take the whole inequality and say we now want where cos squared theta minus pi by 2 is between -1/4 and +1/4. But then if we think about that very carefully, right, if we get a number here, like for cos, and then we square it, then we're guaranteed to get a positive number, right? Because if you think about it, right, if I take any number that's negative, like -2, -3, -4, whatever, and I square it, I always get a positive. So actually, this condition is going to be that cos squared theta, theta minus pi by 2, beg your pardon, is always going to be greater than 0, and it's going to be less than a quarter. Okay, let's even say greater than or equal to 0 and less than a quarter. Okay, so now if we imagine that we square root both sides, we're going to get cos of theta minus pi by 2. Now, what happens as we square root a quarter? Well, we're going to get a half, but we're also going to get plus or minus a half. So now the condition has got to be that we've got to be less than 1/2, but yet greater than -1/2. And I suspect that that's the thing that's going to trip up most people, right? Because if you think about it, if cos squared is less than a quarter, it actually means that cos itself can be anything from -1/2 all the way up to +1/2, because if it was -1/2 and we square it, well, then the maximum value will be a quarter. Okay? All right, then. So essentially, we want to find out this. Now, I think the best way to do this is to use a graph. And before we do a graph, I'm going to use a substitution. I'm going to say let u equal theta minus pi by 2. So that means that I want to think about cos u being between -1/2 and +1/2. Now, I know many of you think that's making things unnecessarily complex, but the thing is, right, I'm going to use the graph to explain what's going on in a second, and I think it really helps if we're just dealing with the graph of cos u, makes things a lot simpler. Okay, so let's draw the graph. Okay, so this will be like pi by 2, pi, 3 pi by 2, 2 pi. And over here, this would be like -pi by 2, and -pi, and so on. And the cos graph goes between +1 and -1, right? So if I was to draw the cos graph, we remember that the cos graph starts at 1, so the graph is going to look something like that. Okay, something like that. Sorry, it's not super smooth. And it's going to come down. Okay, should be a bit better. It's going to go down like that. It's going to go down like that. It's going to come up again. And it will come up like that. Okay, so here we've got a graph of y is equal to cos u, I guess. And what do we require? We require that cos u is between +1/2 and -1/2. Well, let's draw the graph of y is equal to 1/2. That's going to be like that. And then the graph of y is equal to -1/2, right? That's going to be sort of like that. So here's +1/2. And here is +1/2. And here is -1/2. So if cos has got to be between -1/2 and +1/2, then basically what we're saying is we want this part of the graph, like that bit there, and this part of the graph, and this part of the graph, right? So what we want to do is want to find out what those values are. And so in order to find those values, we want to find these critical values here and here, here and here, here and here. Now, if we do cos inverse 1/2 in our calculator, then what we're going to get here is we're going to get pi by 3. And that means via symmetry that this is going to be -pi by 3. Okay, so that's going to be -pi by 3 there. And again, by using symmetry, we should also be able to figure out what this value is here, because it's kind of symmetrical about this point in a way. So the distance between pi by 3 and pi by 2 is pi by 6. And so the distance from this pi by 2 to the next value is also going to be pi by 6. So I've got to do pi by 2 plus pi by 6, and that will give me 2 pi upon 3. Right, so 2 pi upon 3. Now, if you're not sure about that, right, pi upon 2 plus pi upon 6 is equal to 3 pi upon 6 plus pi upon 6, which is 4 pi upon 6, which is 2 pi upon 3, right? So just showing you that it works, okay? And so again, via symmetry, that's going to be minus 2 pi upon 3. Why am I saying symmetry? Well, because the cos graph, right, is symmetrical about the y-axis. So if this is a point at pi by 3, then negative pi by 3 would also be a point. And if 2 pi by 3 is a point, then negative 2 by 3 will also be a point. Okay. And of course, we could have this region here as well, right? So we could take 3 pi by 2 and minus pi by 6 and 3 pi by 2 plus pi by 6. And we would also get those values there. But for the moment, I'm just going to let that be. And I'm going to say that I've got these two ranges that u must be between negative 2 pi upon 3 and negative pi by 3. And also that u must be between pi by 3 and positive 2 pi by 3. And so we've got the ranges for u then. So how are we going to get the ranges for theta, which is what we want? Well, theta is going to be equal to u plus pi by 2, right? Because if u is theta minus pi by 2, then theta is going to be equal to u plus pi by 2. So if you want, right, we could just like replace our inequality with this thing here. So I'll do that. So instead of u, we got theta minus pi by 2. And that thing must be between negative 2 pi upon 3 and negative pi upon 3. And again, theta minus pi by 2 must be between pi by 3 and positive 2 pi upon 3. Okay, well, I don't want to screw up at the end, I think. So I'm going to turn everything into fractions of 6. So this will be 4 pi upon 6, theta minus 3 pi upon 6. And minus 2 pi upon 6. Okay, and same thing over here. So 2 pi upon 6, theta minus 3 pi upon 6. And that will be 4 pi upon 6. Yep, I think that's right. And so then what I've got to do is I've basically just got to add 3 pi by 6 to the whole inequality. So if I do that over here, I'm going to get negative pi by 6 theta and pi by 6. And if I do the same thing on this side, I'm going to get 5 pi by 6 theta and 7 pi by 6. And I just want to check that those are within the range of values that we're asked for. So we're asked between negative pi by 6 and 7 pi by 6. Yeah, so that should fit. So the last thing I'm going to do is I'm going to check the mark scheme, make sure that I'm right. Yeah, okay, that looks good. Okay, so they say excluding 0 and excluding pi. Okay, I just got to quickly think to myself why that must be the case. So give me 1 second. Yeah, okay. It's kind of obvious now, actually, if you think about it. Remember the common ratio R is equal to, what is it? Where was it? 4 cos squared theta minus pi by 2. Right? 4 cos squared theta minus pi by 2. Well, in order to have a geometric progression in the first place, right, we require that R cannot be equal to 0, right? Because if the common ratio is 0, right, what is our geometric progression going to be? It's going to be 0, 0, 0, 0, 0, 0, 0, right? You know, which isn't really a geometric progression. So we kind of want to solve when this is equal to 0, right? So cos squared theta minus pi by 2 is equal to 0. So cos theta minus pi by 2 is equal to 0. So if we invert that, then we're going to get theta minus pi by 2. Well, when is cos equal to 0? It's equal to 0 at pi by 2 and at 3 pi by 2 or minus pi by 2 as well. Just using the graph, right? So if I go back to the graph, right, where is cos equal to 0? Cos is equal to 0 here, here, here. Okay. So then theta is either going to be equal to pi by 2 plus pi, which is pi, or minus pi by 2 plus pi by 2, which is 0. So we can't have those two things, basically. So we end up with these two solutions. So let me kind of highlight it. So we end up with this, right? And this one, except theta cannot be equal to 0. And we've also got this solution here, right? Except theta cannot be equal to pi. Okay, so there's quite a lot to think about there, guys. I think, and that is not an easy question. It's quite complex, really. But can I just make some recommendations to you? So I think that drawing nice, clear graphs, right, really breaks down the problem, helps you to understand what's going on. I think that's kind of the first thing that I would say. I think using a substitution means that even though you've got a tiny bit more work, in the end, it's not actually that much more work, and it means you're more inclined to get it right, I suspect. The other thing I would say is, you know, once you got your values here at the end, right, and obviously you're not like me, you can't look at the mark scheme in an exam, but let's say that, you know, you want to check that you're right. What's the best way of doing that? You just take values within these ranges, right? You substitute them into the expression for r, and you see if you get a value that is between 1 and -1, right? If you do, then it seems to be confirmation that you're probably right. If you get a value that's not between 1 and -1, then you know that you've gone wrong. Okay, so that's what I would recommend. Okay, now, of course, that question is targeted towards the people who are going to be wanting their A stars and close to 100. So if that's you, you want to be really plugging away at that. And I would say that, you know, this question really tests your analytical, your problem-solving skills. And so it is actually a very useful thing as you move forward to your A level and later to your degree to be able to do this kind of thing, right? So I think it is really worth just learning that skill of how to analyze and to be precise. Okay, now I hope this was helpful. If you're finding these videos good, please give a like, a thumbs up, subscribe, and share with your friends. See you next time.